Here's part 2, continuing with the first lowest tech derivation of the vector triple product identity. So we've shown, here's the picture I promised last time. What we've got is we've got two vectors b and c. Let's suppose they're in kind of a horizontal plane. Then the cross product b cross c is going to be orthogonal to that. That's the green. And then, so let's suppose we have some vector a. Then we're crossing that with b cross c. And I just want to observe that the result of that, the vector triple product, it definitely has to be perpendicular to b cross c, so it's going to be back in the red plane. But it's also perpendicular to a, so it's going to be in a blue plane. I'm kind of thinking of that as slanting kind of up and to the right. And then the intersection is that line that they're they're intersecting. So it's in both those planes, so it's going to be on that line of intersection of those planes. Okay, so with that picture in mind, let's go on to number 5. Suppose that B and A are actually perpendicular. So maybe move A around a bit until that's perpendicular. What's going to happen? The claim is that A cross B cross C is therefore collinear with B. I think this is where one of the more subtle things about this phenomenon. Okay, we know that from the previous part that A cross B cross C is going to be in the intersection of the plane of two planes. Okay, it's going to be in this line that's the intersection of the all things perpendicular to A and all things that can be made out of B and C. Well, what if B is already perpendicular to A? Okay, so in this case, the vector B is already in the desired intersection, which is a line. Now let me see if we're being careful enough. The intersection of two planes that all go through the origin, it can either be a line or it could be a plane if the two planes are identical. But what's the only time the planes are going to be identical? That's when A is parallel to B cross C, and we know that that's when the cross product is actually 0. Okay, so let's not worry about it. That's the trivial case where it's 0. Otherwise, the intersection really is a line, and if B is perpendicular to A, B is already marking out the direction where these things have to be. Okay, so the triple cross product must be collinear with B. Okay, and of course similarly, if C is perpendicular to A, let's just change that to a C, then this guy is collinear. Just to make sure we are clear what that means, A cross B cross C is collinear with C. Okay, oops. Okay, that's really, really powerful. Okay, so now we can actually guess the formula in just the next couple minutes before we end this video. So A cross B cross C. What's going to be another way to write that? It's got to be equal to some mystery formula of this form, I claim. So why don't you go ahead and read 6, pause it and read 6, and then see what you can do. Or you see if you can convince yourself of 6 and even go on to 7. So it must be given by some formula that's some combination of B and C with some mystery coefficients. And I put a minus sign in here in particular on purpose because of the antisymmetry. Okay, so mystery 1 should be some term that vanishes if C is perpendicular to A. So it's a scalar is what I mean. It's a scalar combination of B and C. Some scalar built out of A, B, and C. And it should vanish if C is perpendicular to A. Why is that? Remember, that's what we got in number 5. If C is perpendicular to A, then A cross B cross C should not need any multiple of B. It should just be a multiple of C. And similarly, mystery 2 should vanish if B is perpendicular to A, because in that case we only need a multiple of B. Okay. We also want the formula to be antisymmetric if we switch B and C. Okay. Well, that's going to be pretty automatic if we kind of make mystery 1 and mystery 2 the same if we switch B and C, given that I've put a minus sign in already to try to enforce the antisymmetry. So we need two very similar kinds of terms that take sum of this vector information, give me a scalar, and it's supposed to vanish if these things are orthogonal. It's hopefully, if you remember how the geometry and algebra relate for the basic vector algebra operations, you should be able to get it here, that A cross B cross C, that mystery 1 should be nothing other than the dot product. And it's a little surprising seeing the dot product come in, but what we're seeing is it's all about things being perpendicular, and this is the only thing that's going to possibly have the right property. Okay, so that's going to be, A dot C, and then the other one should be A dot B. That will indeed have all these properties. It's going to vanish in the right way, and it's going to be antisymmetric. Let's see. Yeah, if you switch B and C, then these guys just switch roles, and then the minus sign makes it antisymmetric. If B and C are exactly the same, it's obviously 0. It's not too hard to see if B and C are collinear. If B and C are just multiples of each other, it's not too hard to see that vanishes. That should be most of it. Oh yeah, and of course it's a linear combination of B and C. It's not absolutely obvious right from the just by staring at it that it's also perpendicular to A. But if you dot this with A, what you get is A dot C times B dot C minus A dot B times C dot A. Well, it's the same thing. And so that again vanishes. Okay. So this pretty much cannot fail. This must be the right answer, except there's a couple of issues. One is we might not have the sign. Okay. And of course, the big thing is it's trilinear. Okay, it's trilinear. It's easy to show that if you scale A, B, or C, then it's the scale factor comes out. Or if I put in an A plus A prime in here and an A plus A prime in here, then it's all gonna come out. You could check that if you want, but it's really anything built out of just multiplying and adding and subtracting really should satisfy those distributive law or trilinearity properties. So the only thing is we might be messed up with the sign. And it's conceivable that there's like a 1/2 or a 2. It's unlikely there'd be a pi or root 2 or a 6 or something like that. But we need to check. Okay. So the thing to do, of course, is to be really sure. We know that even regardless of all these other fancy things, 2 through 5, if just knowing the trilinearity, we know that we could just check this with the 27 possibilities I, J, and K. Now, given that we've already checked those properties, though, given we've checked the antisymmetry and the fact that like when B and C are the same vector, it's going to vanish, you really don't have to try that many. Okay, so I won't show them all, but you could certainly look at, for example, I cross J. That alone will make sure we get the sign right. Okay, is this equal to? We'll put in the I and then J. I don't know why that wasn't bold. And then this is I. And then A dot B is I dot I. And then that's J. Okay. Well, the left-hand side is I dot K, or I cross K rather. I cross K. That's minus J. And indeed, that's what we get on the right-hand side. The right-hand side, I dot J vanishes, and then the sign gives me minus J. Boom. Okay. So now we're pretty confident that even the sign is right, and that there's no weird overall scale factor. Okay. So you just have to plug in. You try I, J, and K here. You never have to have these be the same, and you can also always have them in alphabetical order, because I don't need to try J cross I. I've already checked that if I switch the order, this is already good. I checked that in a much deeper way, much more general way than just trying I's, J's, and K's. Okay, so that's a good place to stop here. Let me just go ahead and show you the rest of it, in case you want to look at part of the rest of it before I start the next video.